Hello everybody. In this video we're going to start a new topic in Aspen Plus, which is the heat transfer equipment. And by this we mean the heat exchangers. Before we go and see how we can do the calculations and stuff in Aspen Plus, I would prefer to keep this video as a review, just to cover the main points that I believe must be well understood before we start to work with Aspen Plus. So I'll do my best to make this as short and precise as possible, and to cover the main points that I am interested in. The heat exchanger is a very well-known piece of equipment. It is used to exchange the heat between two fluids, and it can be used for cooling and heating, and there should be a barrier between the two fluids so that it allows the heat to be transferred without the mixing of the two fluids. The choice of the type of heat exchanger can be dependent on many things. It may depend on the type of the fluid, the process, is it cooling or heating, the duty that we want to achieve, the available space, the properties of the fluids, and the accessibility for cleaning and maintenance. And we will see in the next few slides why these parameters affect the choice of the heat exchanger. But first, I'd like to talk about the types of heat exchangers that we face. So there is a type that's called double pipe. It's simply as its name implies, it's just two pipes, two concentric pipes. One fluid is flowing inside the inner pipe, and the second is flowing in the annulus between the two tubes or the two pipes. The shell and tube heat exchanger is kind of similar, but instead of having only one tube inside, we will have a tube bundle. It's a set of tubes that is arranged as we see here inside this big shell. And this of course offers larger heat transfer area than the area that we have here available in such case. There are the finned heat exchangers, and they are not like these in the sense of having two fluids flowing inside a place or a specific place in the heat exchanger. But here we have the fluid of interest that we want to cool is or cool down is flowing in the tubes, and just to make sure, and we're using air to cool it down, but instead I mean for the sake of increasing the surface area, there are fins that are added just to increase the area and increase the efficiency of heat transfer. There are air coolers, and these are used in industry a lot in case of having utility water like cooling water or heating water, and this water is required to be cooled down so that we can reuse it, and this is cooled down by air. So there is a big fan, and the air or it can be natural drift or forced drift, depending on the type of the air cooler. But it's kind of evaporative cooling kind of thing, or kind of heat exchanger. It depends on the evaporation of some of the fluid to cool down the rest of it. The condenser and reboilers are kind of similar to the shell and tube heat exchangers, but they are kind of special types, and they are used a lot. And the very famous application for these two is the distillation column. So you have the condenser at the top of the column and the reboiler in the bottom of the column, so that we will have a continuous flow of gas and liquid all over the length of the distillation column. The heat exchangers that we talked about will have different, what we call the heat exchanger density or area density. And this is how much area is available for the unit volume. And as we get higher area per unit volume, this will make the heat exchanger more compact. In many cases, we have limitations in space, and we will have limitations in the area that we have. And in this case, we will require very compact heat exchangers so that we can achieve the required heat transfer in this limited area. Now we go talk about the configurations of the heat exchanger, how we can make the regime of the flow. So in some cases, we'll have the cross flow. In this case, the cold and hot fluids are making like a cross shape, like what we see here. In the counter current, the co-current or parallel flow, the two streams are flowing parallel to each other in the same direction. The counter current are parallel but in opposite direction. Of course, each one of them might have some advantages over the other, but these two are kind of more used in like as pure counter current or pure co-current. We will see in in shell and tube heat exchanger sometimes this is the case that we face. It's not a pure counter current or pure co-current. It's closer to this shape. But just to understand what the difference is, it's good to take a look at the temperature profile. So this is the co-current and this is the counter current, and in the parallel flow you'd see that the start of the flow, which is the same point here, we have the highest temperature with the lowest temperature. So there is a very high driving force here, and the driving force decreases as we go forward until we reach the end of the heat exchanger, where we will have the least driving force. So the heat transfer here is not going to be as fast as the heat transfer in this case, but in the counter current you'd see that it's working the other way. So the hottest fluid is transferring heat to the highest temperature. So you'll have here good driving force, and here we'll have a driving force, and this is the beauty of the counter current is that we have continuous driving force all over the heat transfer area. This is the same theory that you can apply to the mass transfer in case of extraction, in case of distillation, in case of stripping, absorption, whatever. In these cases, you would see that the counter current is always more efficient. We have already talked about this, so I'm not gonna talk about it anymore. There is one kind of heat exchanger which is being used but not as widely as the shell and tube heat exchanger, which is the plate and frame heat exchanger. And this is, as you see here, it's composed of just plates, and they can be added as many as you want. So you'll add a plate and then a plate, and they are very flexible for in the sense of the ability of addition or removal of plates, and controlling the area of heat transfer. And of course it's easier in maintenance and in cleaning, because it's very easy to assemble and disassemble. Just to understand how it works, because it seems here like a complex or hard to understand figure. So in this figure you can understand how it works. So we have like some grooves here, and these grooves kind of tell the fluid where it's gonna flow between the plates. And the way it works is that we have a hot fluid flowing between the two plates, and then a cold fluid between the next two plates, and then a hot and then a cold fluid, then cold and hot, and so on. So each fluid is transferring heat with the two fluids on the other side, or on the two sides of the plate that this fluid is contacting, and that's why it's kind of very compact and very efficient heat transfer material, or heat transfer equipment. And now let's talk about the shell and tube heat exchanger. It's a very widely used and very famous heat transfer equipment. And it's, as we mentioned before, it consists of tubes where a fluid is flowing in the tubes, and this is a shell where the other fluid is transferring. This is the area of heat transfer here. And the area of heat transfer is the external area of the tubes. And you'll see that there are some baffles here, and these baffles are used to kind of make the flow. And this is what I was mentioning, that the flow is kind of more like a cross flow in the case of baffles, because the flow is going perpendicular to the tubes back and forth, and this increases the turbulence, and this makes the heat transfer more efficient. The just to make sure that everybody has the sense of the heat transfer, or the shell and tube heat exchanger dimensions. The shell and tube heat exchanger can be as big as what you see in these figures and might be larger. So in this case, this heat exchanger, the diameter of the shell is around 3 meters. As you see from the scale with these two guys standing up here, and it's almost double their length. And there are many tubes in there. This is kind of very sophisticated piece of equipment. You'd see that the tubes are a lot of tubes and then held with the buffles, and then it's all put inside the shell. And you see here there should be a crane to hold it and make sure that it is there is enough space so you can have all the tube bundle, and then to push it inside the shell. And this is kind of routine thing that's being done in maintenance, so that you can it can be cleaned and can be checked in case of errors or problems with the operation. The shell and tube heat exchanger is usually defined using two numbers, which is the number of shell passes and number of tube passes. And by the passes is we mean how many times the flow is flowing in the shell or in the tube in a specific direction. So it's in this case we'd see that the flow in the tube is gonna go like this, and then go to the tubes, and then change direction, go back here, and then comes out. And this is one pass and then two passes, so it is two tube passes. In the shell, although it's going up and down because of the buffles, but it is going in one direction, which is from here to there. So this is one shell pass. In this case, it has buffles, but it's going and then coming back and then coming out of here. So it is two shell passes and four tube passes. So when I say 1 2 heat exchanger, I know it's one shell pass and two tube passes. 2 4, it's two shell passes and four tube passes. The heat transfer in the heat exchanger happens in different modes. So there is a convective heat transfer in the tubes and in the shell. And this is what we describe, or the resistance of heat transfer is described by 1 over HA and 1 over HA, I for inside and O for outside the tubes. And this is the resistance by conduction through the tubes itself. And we use what is called the overall heat transfer coefficient just to describe the summation of the heat transfer in the shell and in the tubes. Usually we ignore this term because of the thermal conductivity of the tube material is high, so we don't usually consider this as a resistance or a big resistance compared to these two resistances. Uh, Usually the heat transfer coefficient is, or the overall heat transfer coefficient is function of the two fluids. So you can find tables like these, and in the table you just find what the two fluids are, and is it oil to oil, then you would use this number. If it is water to air in fin tubes, it's this number. So it is highly dependent of the type of the fluids that we are exchanging heat between. One more thing we want to talk about is the fouling, and the fouling is some stuff in the fluid, or it's a property of the fluid that contains dirt, contains salts, or whatever material that can be deposited at the operating temperature. And this fouling is kind of big problem because in general the fouling is like an insulating material that deposits on the tubes, so it reduces the heat transfer in the heat exchanger, which reduces the efficiency of the heat exchanger. And in some cases, in case of high fouling material, this might block some tubes. And as you see here, the tubes from outside are kind of very dirty because of the fouling that took place in this heat exchanger. And that's why in the heat transfer coefficient or the overall heat transfer coefficient, we should take into consideration that there is a term for fouling inside and outside the tubes, and that's why we have what we call the U design, which is the design heat transfer coefficient, not just the overall heat transfer coefficient. So this is important to make sure that this is not gonna mess up with the equations and the design that's being done. This table shows some materials and or some fluids and the fouling factor that is being used in each of these cases to be used in the design of heat exchanger. The last point that we are going to talk about is the routing of the fluids. And to understand what we mean routing is which fluid is going to flow in the shell and which fluid is going to flow in the tubes. I just want you to take a look at these photos first, because we see before we see the or talk about the routing. The fluid that's flowing in the tubes is gonna be contacting only the tubes. It's gonna flow in the tubes. It's not gonna see any other tubes or any other material. I'm sorry. While the fluid flowing in the shell is gonna be contacting the tubes from outside and contacting the shell from inside. So it's flowing in here, contacting the shell and the tube. And this is pretty important point, because it's gonna affect the routing of the fluids. So what we would see that in case of corrosive fluid, high fouling fluid, the high pressure fluid, we would prefer to route them in the tube side. And just to think about it, if you have a corrosive fluid, like an acid or a base or something like that, then you should use a material that is resistant to the corrosion, which is going to be an expensive material. And in case of flowing in the shell, you have to make sure that the material of the shell, the material of the tubes, the baffles, and all the metal parts inside that are contacted by the fluid in the shell are made of this corrosive material, resistive material, which is expensive material. So it's better for this to be routed in the tube side. Again, the same for the high pressure fluid. High pressure fluid require thick tubes and thick shell, and that's why you would prefer to put it in the tubes, so that we can use only tubes with thick or higher thickness, which is not going to be very high thickness, by the way, compared to the increase in the thickness of the shell because of the high diameter. And the same for the fouling. In case of the fouling or fluid that has a lot of fouling, it's very, very, very tedious and difficult to, if it's possible, to clean between the tubes from outside. Inside the tube, in a case like this, there are some materials like the drilling machine and stuff like that that can that can has a bit like a brush and can clean this fouling inside. But in case of between the tubes, it's not possible. It's not easy if it's possible, because in some cases it's not even possible to do that. So it's better to route the high fouling fluid in the tubes. In case of higher flow rate fluid, and let's assume we have two fluids with different flow rates, then it's better for the high flow rate fluid to go in the high area. And this is because routing the low flow rate fluid in the large area will result in low Reynolds number and low heat transfer coefficient. So it's not going to be a good way of operating the heat exchanger, and it's going to have a negative impact on the heat transfer efficiency. So the higher flow fluid is better to be routed in the higher area, which is the area of the shells. If you have a vapor, evaporating liquid, or condensing vapor, then it's better to put it in the shell, because the vapors usually have higher volume than the volume of the liquids. In case of viscous fluid, it's better to put it in the shell side because of the larger area. The viscous fluids will generate a lot of pressure losses due to the viscosity. So it's better to provide larger area so that the viscosity or the viscous losses will not be high. So this is like the main points that we should consider when we route the fluid in the heat exchanger. There might be cases where conflicts will happen. So maybe you have a corrosive fluid that has high flow rate. So if you apply this rule, then it should go into the tube side. But if you apply this rule, it should go into the shell side. So this depends on the economic studies and other stuff. But these are the rules of thumb, if you can say that. In the next video, we'll see the shell and tube heat exchanger design steps briefly, just to make sure that we understand the steps and how much time it takes and how easy to do this using Aspen Plus. So this is going to be the topic of the next video, inshallah. So I'll see you then. Goodbye.